We were talking about chiral molecules and how to identify which of the different enantiomers we're looking at. And we need to be able to assign priorities to the groups. And so these are the rules for assigning priorities. The atoms bonded to the stereogenic center, and they have to be bonded directly. The atoms bonded directly to the stereogenic carbon or the chiral carbon are ranked by atomic number. So high priority in this example would be the chlorine, then oxygen, carbon, and hydrogen. Yeah, it's that new compound I invented, carbogen. If there are two or more atoms that are the same, like in this example here, here's the stereogenic center, and if we have a carbon for an ethyl group and a carbon for a methyl group, how do we decide which is more important? The larger one, you go to the next atom. So here's carbon, you find the next biggest atom that you can, because there's hydrogens here, but this one's also bonded to a carbon. So this carbon is bigger than anything attached to that carbon, which is all hydrogens. Basically, you can look at this alkyl group, and the bigger the group, the higher the priority. In cyclic compounds, we use the same rules for deciding. So looking at this stereogenic center, we've got a hydrogen. He's going to be the lowest priority. And then we've got one carbon. And then we're going to look in this direction. We encounter one carbon, two carbons, and the second carbon has multiple carbons attached to it. Going this way, we've got one carbon, and so this carbon is equivalent, the same distance as this one from that center that we're looking at, but this one only has one carbon and two hydrogens bonded to it. This carbon has 1, 2, 3 other carbons, so this guy would win. Does that make sense? It looks good in my mind, but I don't think when I talk about it, it comes out very well. Let's try it this way. Maybe if we kind of draw like a train of atoms. So we're looking at going in that direction. What are we encountering? Well, first we're encountering a carbon, and then another carbon, right? So here's, what am I pointing at? There's first carbon, and here's the second carbon. This carbon has these two guys attached to it, so like that. And then it goes on around the ring, right? 1, 2, 3 carbons before we come back and grab the tail. 1, 2, 3. Does that make sense? Do you see what I'm doing? Bless you. Someone's allergic to that. It's okay. And so I changed the color, and it didn't change the color. I need to order some more styli. Styli, is that what it would be? So going this way, what do we encounter? Well, first we come to a carbon, and then another carbon, and then another carbon, and then this carbon that has 2 carbons attached to it, and then continuing on around, here's this one, and then we're back to where we started from. So in comparing these two groups, this is where they are attached. So here we come to a carbon, and here we come to a carbon and a carbon. And so at that point, they're the same. But the second carbon, what's attached to it is different, because here this one has some hydrogens on it and 1 carbon. And so here from this carbon, we can go 3 different carbons. And so these have a higher priority than this one. Does that make sense?
What do we use that priority for?
We use the priority for deciding if this is a right-handed or a left-handed chiral center, stereogenic center, and identifying the difference. Right now we're just looking at how to assign the priorities. Does that make sense? The cyclic ones are a little trickier because it looks like, well, I'm attached to the same thing. Yeah, but you're attached to different parts of the same thing. Going around this way, we encounter larger atoms first before going around this way takes longer to get to those larger atoms. So assign a priority order to each of the following sets of groups. So the line here indicates where the group is attached to the chiral center. And so first we're going to look at the first atom. We have carbon and hydrogen and nitrogen. Which of those atoms has the highest atomic number? Nitrogen, right? So nitrogen is going to be number 1. So this is going to be number 1. And hydrogen is going to be number 4, because that's the smallest atom. And then we have to decide between these two guys. This carbon has 3 hydrogens attached to it. This carbon has a hydrogen and 2 other carbons. So this guy is more important, he's bigger. So he's number 2, and this guy's number 3.
Why is it that the nitrogen has higher priority than the number 2?
Because that's what they decided to do.
Even though there's more mass on the...
Yeah. They decided to do it this way. It really doesn't matter as long as we all agree. And this is just how they decided to do it. I think because it's easier. You don't actually have to calculate molar masses or anything. You just look at the first, we're going for the first difference. So you look at the first atom. If those were all the same, then you have to look at the next one that's connected. But looking at the first one, we go with highest atomic number, just because they decided. So let's look at B. So we've got oxygen, bromine, carbon, and carbon. Which of these has the highest priority? The bromine, right? Because bromine's a large atom. And then what's the next smallest, oxygen or carbon? Oxygen. So oxygen's going to be number 2. And then we're deciding between these 2 carbons, which one is going to have a higher priority? The CH2OH, right? Because this carbon is bonded to a hydrogen. And so this guy's going to be number 4. Is it beginning to make a little more sense? Let's do letter C. We've got oxygen, nitrogen, carbon, and oxygen. Which of those elements is the highest atomic number? Oxygen. So we have to compare. This oxygen is bonded to a carbon. This oxygen is bonded to a hydrogen. Which one has higher priority? The one with the carbon. So this is number 1, and this last guy is number 2. And then we've got carbon and nitrogen. Nitrogen is the next largest atom, next highest atomic number after oxygen, and then this guy is 4. See, I think just being able to look at the N and the C and not having to deal with the rest of the mess of these groups makes it easier. And I think that's probably why they did it that way. Any questions yet? Okay, letter D, it's all carbons. So here's carbon, and the second atom in the chain is a carbon. Here the second atom is carbon. Here, this one has how many carbons attached to it? 3. And this one has how many? 2. So this one having more carbons attached directly to that first atom is going to be the highest priority. This one, because it has 2 carbons attached directly to this one, is going to be the second priority. And then which of the remaining 2 is going to be next highest? The first one. So that's 3 and this is 4. Because this guy goes carbon, carbon, carbon before you have to go to a hydrogen, and this one goes carbon, carbon, hydrogen. Okay? If you encounter multiple bonds, you treat them as if they were an equal number of single bonds. So this vinyl group, if this was one of the groups we were looking at, and here we have it in a, this is how we would think of it. We would think of this double bond, that's a carbon to a carbon for one of those, and carbon to carbon for the other. And so we think of it like this. We treat this one as if it's bonded to 2 carbons, because it's bonded twice to 1 carbon. We're not actually taking this double bond apart, but this is how they've decided to count it. So we're treating this carbon as though it's bonded to 2 carbons, and we're also treating this carbon as though it's bonded to 2 carbons, because this one is bonded twice to that carbon. We would treat this guy down here, a triple bond. We're going to say, okay, that carbon is bonded 3 times to this carbon. We're going to treat it like it's bonded to 3 carbon atoms. And this one likewise is bonded to 3 carbon atoms. Over here we've got CHO, CH and a double bond O. So this carbon is bonded to a hydrogen and to oxygen twice. So CO and CO, and this oxygen is bonded to 2 carbons. And that's just for the purposes of assigning priority.